Today what we're going to talk about is the future of the TxDOT Roadway Design Manual. The table of contents, we're going to talk, these are some of the items we're going to talk about today. Reduction in FHWA design controlling criteria, innovative intersection guidance, which will be fun, right turn slip lane guidance, HOV guidance as a result of Senate Bill 312, which recently passed, and a sample DHV calculation to provide some clarification. The first thing we're going to talk about is the FHWA reduction in design controlling criteria. Currently, there are 13 design controlling criteria. Now, as a result of Research Report 783, which used the Highway Capacity Manual and Highway Safety Manual to examine existing controlling criteria, FHWA reduced the high-speed NHS controlling criteria from 13 to 10. The three that were removed were the lateral offset to obstruction, which is already covered under shoulder width in rural areas, and really it's most relevant to urban areas and did not rise to the same level of effect as other controlling criteria. Vertical alignment, crest vertical curve design is already covered under stopping sight distance. Grade is already explicitly covered as a separate criteria. Sag vertical curves, research determined no relationship to the effects on crashes. Generally, sag vertical curve length is not critical in daytime when drivers can see beyond the sag vertical curve, nor at night when vehicle taillights and headlights make another vehicle visible, enter beyond the sag vertical curve. And also the third one that's being removed for high speed is bridge width. Research determined little relationship in crash frequency, and lane and shoulder width already apply to bridges, so this is already covered by other controlling criteria. So on the left here, you see the original 13 existing FHWA controlling criteria, and on the right, you see the remaining 10, and the three at the bottom are going to be removed in the future: bridge width, vertical alignment, and lateral offset to obstruction. For NHS low speed, only design speed and design loading structural capacity would remain as FHWA controlling criteria. The research indicates that the current controlling criteria are less influential on the traffic operational and safety performance of low speed urban and suburban arterials than other features such as intersection design and access management strategies. And these are the original 13 controlling criteria with the two remaining on the right: design speed and design loading structural capacity. Now we're going to talk about some of the updates that are coming to Appendix E of the RDM, which will be innovative intersections. Some of the innovative intersections that guidance will be provided on will be roundabouts, DDIs, MUTs, R-cuts, and DLTs. And I'll go through each one of these as we go through the presentation. What are innovative intersection designs? They're designs that eliminate, relocate, or modify conflict points by improving the way the traffic makes certain movements. Safety. The key point is it reduces your conflict points for both vehicles and pedestrians. So there's significant before and after reductions and severity for crashes. Mobility. Typically there's reduced delay, reduced congestion. In the value, typically you can do these in less right-of-way and decrease construction costs and quicker implementation. The first innovative intersection we're going to talk about is a roundabout. A roundabout is a type of circular intersection with yield control of entering traffic, islands on the approaches, and appropriate roadway curvature to reduce vehicle speeds. Why would you consider a roundabout? Well, it improves safety, reduces congestion, reduces pollution and fuel use, and saves money. The key point with the roundabout is you see on the right, your typical intersection, of course, has 32 vehicle-to-vehicle conflict points. The roundabout reduces those to 8 vehicle conflict points, and what this does is it almost eliminates completely the head-on and the high-speed right-angle collisions, which are your more serious collisions at a standard intersection. So what are some of the improved safety benefits? Fewer conflict points, more than 90% reduction in fatalities, 76% reduction in injuries, 35% reduction in all crashes, Slower speeds are generally safer for pedestrians as well, so you have a 30 to 40% reduction in pedestrian incidents and 10% reduction in bicycle crashes, and a 30 to 50% increase in traffic capacity. The primary source of the updates to the RDM in Appendix E will be NCHRP Report 672 and NCHRP Synthesis 488, Roundabout Practices. Consideration for roundabouts for locations that meet or nearly meet signal warrants and proposed all-way stop control intersections. And these will have urban, suburban, and rural applications. And the typical design vehicle would be a WB67, but obviously this could be very dependent as a function of the roadway. So here you have 3 roundabouts. You have your mini roundabout here, your single lane roundabout, and your 2-lane roundabout. Your mini roundabout has a splitter island, which is typically mountable or striped. And in the green, you can see where the pedestrians cross. All 3 of these have a splitter island, which provide a pedestrian refuge. And for the mini roundabout, typically the ICD, or inscribed circle diameter, is 90 feet or less. The ICD for the splitter, for the single lane roundabout here is typically between 90 and 180 feet. And for the 2-lane roundabout, it's 150 to 300 feet. And these are some of the design controlling criteria for roundabouts. Your typical design speed for the mini roundabout is 15 to 20 miles per hour. For the single lane roundabout, about 20 to 25 miles per hour. For the multi-lane roundabout, 25 to 30 miles per hour. And as I said earlier, your typical inscribed circle diameters, 45 to 90 feet for the mini roundabout, 90 to 180 feet for the single lane, and 150 to 300 feet for the dual lane roundabout. And this is an important point that will be emphasized in the update to the RDM. Single lane roundabouts designed for low speed operation are one of the safest treatments available for at-grade intersections. Drivers have no lane use decisions to make. Pedestrians cross 1 lane of traffic at a time. Roadway speeds and widths are low enough to allow comfortable mixed bicycle and motor vehicle flow. And this is from NCHRP Report 672. Having said that, the preference in Texas is going to be to maintain a single-lane roundabout as long as possible. If a single-lane roundabout is adequate for up to 10 years after the opening year, a single-lane roundabout should be constructed. If a multi-lane roundabout is required after 10 years, the single-lane roundabout should be constructed, having the footprint of a multi-lane roundabout and be designed to be easily retrofitted to a multi-lane roundabout when needed. This was an interesting example that was contained in the synthesis study. This is Jackson County, Georgia, and this was initially a 4-way always stop. And as you can see, they decided to construct a mini roundabout, and they widened the pavement structure here. Obviously, is the first step of traffic control. The next one was constructing the inner island. And then this is a completed roundabout. And I point this particular one out because this was done as a very quick retrofit. And it's a mini roundabout, 90-foot inscribed circle diameter, quick construction. It only cost $63,000 in construction costs. And some of the benefits that were gained from this include reduced crashes, and it reduced the quarter-mile stop queue to an 8 to 10 car rolling queue, which is pretty impressive. So this is a very positive result they had in Jackson County, Georgia. The next innovative intersection I'm going to talk about that'll be in the RDM. What is a diverging diamond interchange? A DDI is a type of intersection that connects a freeway with the major highway. It is based on a modified diamond intersection with the shift in traffic within the intersection to safely and efficiently accommodate high volume left turn movements. Traffic within the intersection briefly drives on the left side of the road to allow left turn movements to occur without crossing oncoming traffic or stopping. How do pedestrians use a DDI? They can, the preferred way is for them to go down the center and they have ample opportunity to do that. Why would you consider a DDI? Well, it can improve safety, improves capacity with two-phase signals, reduces pollution and fuel use, and saves money and efficient during both peak and other times and off-peak hours. This is a DDI in Idaho. This was the first one built in the state of Idaho. And again, you see on the left side here, this is your standard conventional diamond interchange. And you have 10 crossing conflict points, 8 merging conflict points, and 8 diverging, a total of 26 conflict points. For your DDI, you have only 14 that remain, and you can see those listed right there. Fewer conflict points, a reduction in all crashes and injuries, slower speeds are generally safe for pedestrians, 30 to 40% reduction in pedestrian incidents. And this is a relatively new interchange concept, so they're still getting more statistics because the statistics obviously will vary upon the location. Some of the basic elements of a DDI. As you can see, there's a crossover right here. So this traffic crosses over to the other side and then crosses back on the other side of the DTI. You have your reverse curvature upstream of the crossover. Two-phase signal timing, which gives you greater throughput through the DDI. And the left turns do not conflict with the opposing traffic. The left turn making this maneuver, and the left turn making this maneuver right here. Some of the guidance that will be used will be the FHWA DDI informational guide. That's the primary source for the update to the RDM. Typical design speeds range from 25 to 35 miles per hour through the 2 intersection crossovers. Your typical design vehicle will again be a WB67, and you want it relatively flat in order to increase driver sight distance. Some of the geometry points that we want to talk about. This crossover angle right here, you typically want it between 40 and 50 degrees to avoid traffic going up the wrong direction if that angle is too shallow. So 40 to 50 degrees is recommended. Also, for your curvature, both upstream and downstream of the crossover, your typically radii would be 150 to 300 feet. Some of the PED benefits that are involved with the DDI. In this particular case, you can see the pedestrians can cross down the middle and then go back. So you have a very wide space here that can accommodate bicyclists if they get off prior to getting into the middle. So it's very pedestrian friendly. PED crossing of only one direction of traffic allows reduction in PED conflict points. The PED crossing down center allows wide walkway, and two-phase signalization benefits the PED crossing time. The next innovative intersection we're going to talk about is a median U-turn, or otherwise known as a MUT. A MUT is an intersection form that replaces direct left turns in an intersection with indirect left turns using a U-turn movement in a wide median. The MUT eliminates left turns on both intersecting streets. Well, why would you consider a MUT? Well, it reduces conflict points for both vehicles and pedestrians, reduces traffic signal phases, and general increase in safety performance. Here's an example of a MUT intersection. There are no direct left turns allowed from either direction or any direction at this. So the primary movement that's made for a major street left turn, as you can see here, they come through the intersection, they get into a decel area, they have a storage length, and they get into the median U-turn. For the minor street left turn movement, they come over, make a right turn, weave over, and do the same thing and get into the median U-turn. And then to finish out the movement, you have a deceleration in storage length to make that right turn. So this is your movement all the way through the intersection. Your primary source that will be used in the RDM update are the FHWA MUT informational guide. Typical spacing for median opening to main intersection is going to be 400 to 600 feet based on signal timing. And again, the typical design vehicle would be a WB67. The chart on the left shows the median width as a function of the particular U-turn movement that is made. This is inner lane to inner lane to outer lane, and inner lane to shoulder. And on the right, what you see is what is called a loon. If you have an instance where your median width is constrained and you have a more narrow median, you can construct loons at both sides that will accommodate the design vehicle. What are some of the PED benefits of a MUT? Well, again, you have your reduction in PED conflict points. The PEDs don't have to contend with left turn vehicle movements, and two-phase signalization benefits. And the pedestrians have the option of doing a single-stage crossover or two-stage crossing, depending on your signalization. The next innovative intersection is a restricted crossing U-turn, otherwise known as an R-cut. An R-cut is an at-grade intersection with directional medians such that the minor road traffic must turn right and make a U-turn back to cross or make a left turn maneuver. Why would you consider an R-cut? Well, significant reduction in conflict points, reduction in crash rates and crash severity, can improve traffic flow, and can be done at signalized or unsignalized intersections with rural locations with low PED activity. On the left here, you have an R-cut with signal control. So your major street movement makes a standard left turn, and this one is signalized. Major street movement, standard left turn. And your minor street movement has to make the same similar movement that was made at the MUT. It has to make this right turn and come back and go through here. And on the right, you have an R-cut with stop control. Again, the primary sources for the RDM update will be the FHWA R-cut informational guide. Typical spacing for median U-turn to main intersection is 400 to 800 feet. Typical design vehicle, again, will be WB67. And again, here's the R-cut spacing consideration for the minor street movement. Again, you have your lane change, your weave, your deceleration length, and your storage up to where the U-turn is performed. And you have a similar chart that you had with the M-cut. This is the median width as a function of the type of U-turn movement that's desired. And again, you have the ability, if you have a narrow median here, to put loons at both ends to accommodate the design vehicle making that movement. What are some of the PED benefits? Well, you have, again, a reduction in PED conflict points, reduction in cycle lengths when signalized, and the R-cut is better suited for relatively low PED activity. Now we come to the displaced left turn intersection, otherwise known as a DLT. This is an intersection form that relocates one or more left turn movements on an approach to the other side of the opposing traffic. This allows left turn movements to proceed simultaneously with the through movements and eliminates the left turn phase for this approach. Why would you consider a DLT? Well, it reduces conflict points, more green time for major movements, offering better progression, and it's compatible with high volume left turning movements. So again, your left turning traffic here would get into this queue right here prior to the major intersection. And typically this distance here is 300 to 500 feet. And so when you have green time here, the left turn progresses at the same time as the straight through movement. The primary sources for the RDM update will be the FHWA DLT informational guide. Typical distance between main intersections and crossovers ranges from 300 to 500 feet. Here. And again, your typical design vehicle is a WB67. Vehicle path through main intersection will determine the curb line, stop bar line, and the width. And the goal is to provide smooth alignment for traffic and avoid back-to-back reverse curves. This one is good because you have a nice tangent section here which is preferable because you want good alignment to avoid any driver confusion so nobody tries to turn this way. What are some of the PED benefits? Crosswalks at same location as a conventional intersection. The median is used to provide a refuge for two-stage PED crossings. So here you have your refuge islands where your PEDs can do a two-stage crossing. The next type of intersection form we want to talk about is a right turn slip lane. This will be in Appendix D of the future roadway design manual. A right turn slip lane is a form that separates right turning traffic from adjacent lanes and allows higher speed right turns. The right turn slip lane also reduces pedestrian exposure by allowing them to cross the roadway in two stages. It has applications for urban, suburban, or rural roadways. The recommended angle of entry is 70 degrees, which I'll show in the next slide. Curb radius and curb-to-curb width is designed to accommodate larger design vehicles. The striping is used to delineate paths for smaller vehicles. And the crosswalk is located near the middle of the channelized island to allow easier pedestrian crossing. So on the left here, you have a right turn slip lane with your decel lane, and here's your 70-degree angle of entry that's recommended. And you have a recommended 20-foot minimum between the intersecting roadway and where the PED crosses right here. And that's in both cases right here, 20 feet to allow a small passenger vehicle to be able to fit in there without blocking the PED crossing. And again, your recommended angle of entry is 70 degrees here. I'm going to change gears a little bit. We're going to talk a little about Hov Lane Guidance. Some of the sources that will be used to provide the Hov Lane Guidance in the appendix of the RDM are the AASHTO Guide for HOV Vehicle Facilities, the TTI study done in 2005, and NCHRP Report 835, which was just completed in 2016, Guidelines for Implementing Managed Lanes. Now, an important point to make is HOV and hot lanes. Hot lanes are pay toll to use HOV. The 85th legislative session, Senate Bill 312, limits hot implementation on future projects. Senate Bill 312 prevents TxDOT from adding a toll component after September 1st, 2017 to any currently non-tolled HOV lanes, unless the project meets at least one of the remaining 4 exceptions found in Section 228.201 of the Texas Transportation Code. The new limitations imposed by Senate Bill 312 do not apply to a highway or segment of highway being operated as a toll project by TxDOT or an entity under contract with TxDOT before September 1st, 2017, or to a project included in the state's air quality state implementation plan before September 1st, 2017. And there was an additional update that was going to be made to the RDM. And of course, these are not all inclusive. These are just primary updates that will be made in the future. TxDOT updates clarifying the design hour volume computation. We've been asked to update that or kind of go back to the previous description that was there to make it a little more clear. Obviously, your ADT represents the total traffic for a year divided by 365. Design hourly volume is typically the 30th highest hourly volume for the design year. K-factor is percent of ADT occurring in the design hour. Directional distribution, percentage of design hourly volume that is in the predominant direction of travel. T is percentage of trucks, and ET is your truck equivalency factor. So on the next slide, there's a sample calculation. And in this case, the top example is computation of DHV with non-directional ADT, meaning both directions of counts are there. So in this case, you simply multiply your ADT times your K-factor times your directional distribution, and then you multiply by the impacts of the additional impacts due to the trucks. And so in this case, you end up with 557 passenger cars per hour in the predominant direction. Now in the second case, the ADT is only provided in one direction, so you only have a directional ADT. So in this case, the computation is the same, except of course you have a factor of 2 to compensate for the fact that you only have one direction of traffic. And of course, the end result is the same passenger cars per hour in the predominant direction of traffic. Thank you very much.